A bar graph is a common way to present information in a visual format. So in a bar graph, you have a y-axis, which is this line right here. The vertical line is the y-axis. And the x-axis is this line right here, the horizontal axis. So a bar graph shows the relationship between the x-axis and the y-axis. So here, we're looking at basketball players and their heights. So here we have the players, and here we have their heights on the left in feet. So to make this graph complete, so that we can start graphing the heights of these players, we first need to label the y and x axis. So over here we have height in feet. Because we don't have these units labeled right here. These could be meters, centimeters, but in this case it's feet. Height in feet. Then over here we have players. Even though that's pretty obvious, we still need to label each axis. So right here, this is the name of the x-axis, the players, and then we get more specific when we get closer to the x-axis. The same thing here. Vertically, we have height in feet, and then we go over here and we have specifically the different heights. So now we need a name for this graph, and the great thing about a title or a name for a graph is that a reader can quickly look at the graph and determine its content. So here we're going to name this Players' Heights. Because what we have here is a representation of the heights of the different players. So finally, we need to take the information we have right here and put it in this graph. Because although we have the heights of the different players, we want to put it in a graph format because that provides a visual way for someone to understand this information. So for player A, we see that that person is 7 feet tall. So we're going to go over to player A, and then we're going to go up to 7 feet. We're going to draw a line right there and come down like this. And this is why it's called a bar graph, because it's a bar. Now B is 6.7 feet. So we go over to player B, and we notice that 6.7 isn't actually labeled anywhere on here. So we're just going to guess that 6.7 is about right there, a little bit higher than 6.5. And again, we're going to draw a bar. Then player C is 5.9 feet. Again, that's not specifically on here, but we're going to go just below the 6 foot mark. Come down, have our third bar. Then our fourth and final player, player D, is 6.3 feet. So we're going to go a little over halfway between 6 and 6.5 and get right there. Now, you may be familiar with a line graph, where there's plots, points like this, and there's lines connecting the dots. It looks like that. Well, that shows over time how something rises or changes or remains constant. Here, we're not looking at really how something's progressing over time. We're just looking at each player and their height. And it also provides a great way to compare the different players' height. Because right here, you're kind of wondering, okay, how do these players' heights relate to each other? Well, right here, you can kind of visualize each bar right here and how much taller the players are than each other. So you can realize that the difference between player B and player D is smaller than the difference between player A and player C. And although you may be thinking, oh, that's obvious from the information right here, it's much easier to visualize right here in a bar graph. Key science research summaries. When you are evaluating a research summary, pay special attention to the results of the experiment, because the results of an experiment assert whether or not the hypothesis has been confirmed. Now you start off asking a question, and then from that question you form a hypothesis. And then you come up with an experiment to test that hypothesis. So the whole point of conducting an experiment is to find out if you can confirm the hypothesis. So that's why that's so important. And so you're going to find out that information in the results of an experiment. Now, after giving the data from the experiment, the scientist may offer some speculative reasons for the results of the experiment. And so you as a reader need to look out for two things. First thing you need to look out for is obvious flaws. You need to be looking out for obvious flaws in the experiment, because if the experiment has obvious flaws, then you cannot trust that the hypothesis has been confirmed or not confirmed. And then you also want to look out for external influences. In order to be effective, a scientific experiment should isolate the problem with which it is concerned, and so it should eliminate any extra external influences. So if those are there, then it's just confusing the whole process of analysis. And so you should be looking out for obvious flaws and extra external influences. ACT, Science, Conflicting Viewpoints. When studying conflicting viewpoints, you should identify two things. The first being the basic disagreement which is taking place. And the second thing you should identify is the basic question they are seeking to answer. In order to assess the rival claims made by scientists, you must understand the specific points on which they differ. Now, in order to understand the specific points on which they differ, you must understand the basic questions they are seeking to answer. Now, it may be that the rival claims made by the scientists are not in fact conflicting, but are simply two differing approaches to solving the same problem. So that's why it's important that you investigate the conflict here by understanding the basic disagreement, but also understanding the basic question each scientist is seeking to answer, and by that understanding the specific points on which they differ. ACT, Science, Research, Summaries. An experimental science project has 4 basic steps. So you start out with making observations because you have a question you want to answer. So say, for example, our question is, does magnetism affect the growth of plants? And so you ask a question, and then you want to try to come up with an idea of what the answer to that question is. And so you make observations on the growth of plants and what you know about magnets affecting other things, and then you form a hypothesis. Which earlier I was asking a question which led to the observations, but a hypothesis is a statement, not a question. So I might say, magnets have no effect on the growth of plants. And that would be a hypothesis. That's a statement. And a hypothesis can either be confirmed or not confirmed. And so from there, that leads you to your controlled experiment. And so you come up with an experiment to test your hypothesis. So what I might do here is I would take some sunflower seeds and put them in a pot with some dirt, and I'd put some magnets in the dirt with those seeds. Now this needs to be a controlled experiment, which means that we have a control. And so if you're familiar with that, that would just be taking another pot, putting dirt in there, and putting sunflower seeds in there. But this time, not putting any magnets. And so with a control, you're just differing from the experiment by one variable. And so we have 2 pots, and they're just differing by one variable. One has magnets, one doesn't have magnets. Because we have to compare the sunflowers that are affected by magnets with the sunflowers that don't have any magnets around them. Otherwise, we don't know if there's a difference. Then after we conduct the experiment, we form a conclusion. And so to form the conclusion, we have to decide if the hypothesis is confirmed or not confirmed. So notice that I said not confirmed, not disproved. So you confirm or do not confirm a hypothesis instead of proving or disproving it, because you never want to disprove something, because there's always a chance that more information could come out that would confirm your hypothesis. And so instead of saying that something's totally disproved and totally implausible, you can just say that it's not confirmed. In other words, we can't confirm it, but we don't know for sure that it's not true. And so then you form your conclusion from whether you confirmed or did not confirm the hypothesis. And so your conclusion is now fact because you backed it up by experimental data. Now, of course, an experiment can always be fallible, and many popular beliefs once proved by experiments have been now overturned by other experiments, but still when you have a conclusion, you're accepting that as fact because you have backed it up with data. So those are the 4 basic steps of an experimental science project. ACT, Science Data Representation. I want to take a look at what some scientific terms mean. So we're going to take a look at fact, conclusion, cause and effect, model, and scientific law. So starting off, a fact is knowledge or information based on real occurrences. And so you could probably already formulate a definition for fact. Now, when we come to conclusion, it's a little bit different than what you might be thinking. It's the result or outcome of an act or process. So in science, we say a conclusion is when one thing happens, it's what occurs because of that first thing that happened. And so that leads us to the next term, which is cause and effect, which states that every occurrence is connected in a specific way to a preceding event. So if one thing happens, it's because something else just happened. For example, if you see a tennis ball rolling down a driveway, you can infer that something happened to make that tennis ball start rolling. Could have been somebody throwing it, or it could have been the wind blowing it down the driveway. And so, just like with a conclusion, it's the result or outcome of an act or process. The reason you have a conclusion, basically, is because of cause and effect. You have a cause, and then the effect is the same thing as the conclusion. And then we have something called a model, which is a schematic description of a system, theory, or phenomenon that accounts for its known or inferred properties and may be used for further study of its characteristics. So basically, this is a diagram, some type of model that explains something that's happening in science. And so it takes into account what we know about it, and then it can be used to further study its characteristics because it takes everything we know about it and it puts it into some kind of diagram that makes it easier to understand. And then we have scientific law, which is a statement of fact meant to explain an action or set of actions. And so it is generally accepted to be true and universal, and they can sometimes be expressed in terms of a single mathematical equation. And so scientific laws are accepted at face value based upon the fact that they have always been observed to be true. Now, some scientific laws or laws of nature include the law of gravity, the law of thermodynamics, and Hooke's law of elasticity. And so again, a scientific law is a statement of fact. So this is something that has been proven to be true, and since it's always been observed to be true, it's accepted at face value. ACT, Science, Data Representation. A hypothesis is a tentative explanation for an observation, phenomenon, or scientific problem that can be tested by further investigation. So notice I said it's a tentative explanation, and that's because hypotheses are not supported by substantial evidence. Now, the stronger the proof of the hypothesis, the greater its accuracy. Because you have to be able to, for something to be a hypothesis, you have to be able to test it by further investigation. So the more proof you have for this hypothesis, the greater the chance that it can be proven by further investigation. So an example of a hypothesis is if condition A exists, then behavior B will happen. So it's an if-then statement. If this happens, then this will happen. Now, hypotheses are either confirmed or not confirmed. So they are confirmed or not confirmed rather than being proven or disproven, because there's a difference. So you could confirm the hypothesis, which is pretty much the same thing as proving something, or you can say that the hypothesis is not confirmed. Well, saying that something is not confirmed and saying something that is disproved is different. Because if you say something that is disproved, you say there's absolutely no way it can happen. When you say something is not confirmed, you're saying that it could still happen, you're just not able to prove that it can happen yet. Because it is always possible that new evidence will be discovered that could possibly support the hypothesis. And so what you may be gathering from this is that a hypothesis is basically an educated guess. You have an observation, a phenomenon, or a scientific problem that you're trying to explain. So based on what you know, you form a tentative explanation that can then later be tested by further investigation. Now there is something called a null hypothesis, which is a testable hypothesis that is often formulated on the basis of the simplest set of assumptions. So it's based upon something that is very simple, that can, again, be tested to be proven or disproven. ACT Science Research Summaries. When you begin working on a research summary, you should pay special attention to identify the problem of the experiment and the experimental design. So the problem of the experiment is the question that the scientists are seeking to answer. And so in order to conduct an experiment, you have to be trying to answer a question. And so another way to state a question is just a problem, because the problem here is we're trying to answer this question. And so the nature or the characteristics of this problem should provide the structure and the shape of the entire experiment. So it provides structure and shape for the experiment. And so based off of the question you're trying to answer, you come up with an experiment to find the answer to that question. And so that's where experimental design comes in. It's the specific actions and experiments that the scientists perform in order to solve the problem. So you come up with a question and you come up with a way to answer that question. Now, in order to understand the results of the research, you need to understand the rationale for the experiments that have been performed. That's why it's essential that you are able to identify both the problem of the experiment and the experimental design in a research summary. ACT Science Research Summaries. When you are evaluating a research summary, you should take special care to identify the experimental control, which is the standard against which the results of the experiment are measured. In other words, it's the measure of what happens when the independent variable is not manipulated. So in an experiment, you have an independent and a dependent variable. So this is a cause and effect relationship. You manipulate the independent variable, and then you observe what happens to the dependent variable because of what you did to the independent variable. And so what happens with a control is you're not changing the independent variable at all. Because if you conducted an experiment without a control, you would not be able to determine anything from the experiment. You would be able to see what happened as a result of what you did, but you wouldn't have anything to compare it to. So the control is there to give you something to compare it to. So an example is a scientist who wants to determine what would happen to a mouse who is fed a special diet. So the control here would be the mouse receiving a normal diet. So here, the independent variable is going to be the diet, and the dependent variable is going to be whatever happens to the mouse, probably behavior or looks or appearance. And so you're playing around with that independent variable of the diet. And so say you give it a strange diet, and then the mouse acts a certain way, you don't know if that's normal or abnormal. So that's why you have a control, which is the mouse receiving a normal diet, so you can compare the mouse receiving a special diet to the mouse receiving a normal diet. And in order for the results of an experiment to be meaningful, there must be a clear and reasonable experimental control. That's why it's so important, like in this experiment, to have a mouse receiving a normal diet. ACT Science Conflicting Viewpoints. As you study charts, be sure to note the units that are being used. That's extremely important in science because the unit of measure means everything. If you forget to note the units that are being used, then your answer could mean something entirely different, because depending on the units, a very large number may express a large quantity, or a very small quantity. In fact, you may want to spend a little bit of time learning which units of measure apply to which physical characteristics, so that you will immediately know what is being measured when you look at a table of data. For example, you should know that if you see this symbol right here, it stands for kilogram, which means we must be measuring mass. Or if you see a capital L, you should know that it stands for liter, which means we're measuring volume. In addition to having a good understanding of units, you should also practice identifying trends and patterns in various charts and tables. By studying a bar chart, for instance, you should be able to note the trend and the quantity of a given variable over time. So right here, we don't know exactly what we're measuring, but that's not important. You should be able to look at this bar graph and see a trend here. And after looking at it for a couple of moments, you should be able to notice that every other year, the quantity rises. See here, in 1993, the quantity rose from the previous year. Then it remained the same the next year, and then the next year, it rose in 1995, and then again, 2 years later, it rose again. We go 2 years down the road once more, and we find that the quantity rises again. So that's a trend here in this bar graph. So you should be very good at looking at different types of graphs and immediately noticing trends. ACT Science Research Summaries. When you are evaluating a research summary, you should take special care to identify the variables in the experiment. The variables in the basic experiment can be either independent or dependent. So we'll start with independent variables. So the independent variable in an experiment is the aspect of the experiment that is changed by the scientist on purpose. And then you have the dependent variables. So the dependent variable in an experiment is the aspect that responds to changes that are made in the independent variable. So we have cause and effect here. The independent causes the dependent variable to change. And so the independent variable is manipulated by scientists on purpose so that we can see the effect of it on the dependent variable. And so while the independent variable is manipulated, the dependent variable is just observed to see the changes that take place in it. Now, it's important to be able to identify the independent and dependent variables in an experiment. So let's take a look at this example. An experiment exploring how plastic reacts to different amounts of heat. So here, we're taking a look at plastic and its response to heat. So the independent variable here is going to be temperature. Because we're looking at cause and effect here, and we're looking at how plastic responds to heat. And so heat, or the temperature here, must be the independent variable because that's what we're changing around to see how plastic responds. So that leads us to the dependent variable, which is going to be the plastic. Because we're seeing or observing how the plastic reacts to the differing amounts of heat. So again, the independent variable is the aspect of the experiment that is changed, and the dependent variable is the aspect that responds to the changes made in the independent variable. ACT Science Research Summaries. As you read information about an experiment or experiments, realize that you are going to be asked questions about any differences that occur between experiments or scientists. So as you're reviewing this information, realize that anything odd is likely to be asked about. So be on the lookout for anything odd. And then also be on the lookout for any changes. Because these are the types of things that there's going to be questions about. So make sure that as you review this information, you're on the lookout for anything odd and you're on the lookout for changes. So if one of the experiments deals with the duration of lifetimes for various materials, make sure that you take note of the ones that are extremely short or extremely long. And so since those things would be odd because they're extremely short or extremely long, you know that you need to be taking special note of those. So circle them in your answer booklet and be ready to go back and identify them in later questions. ACT Science Research Summaries. As you go over the experiments, make sure you have a high level of understanding of what each one was about. As you review the experiments, the main goals are to get a general understanding of what they were about and notice the key variables that were changed. So by getting a general understanding of what went on and understanding which variables were changed, it'll allow you to save time while answering the questions because you'll be quickly able to go to the right experiment depending on what you need to find out. So if you're looking at 3 experiments during the test, first you want to read these experiments and get a general understanding, and you need to understand which key variables were changed. You might even want to make a note of that, like in experiment 1, temperature was changed. In experiment 2, pressure was changed. And then in the third experiment, volume was changed. And so now you have a general understanding of what each experiment is about. You know which key variables were changed. And so then when you have a question about one of the experiments, you immediately know where to go to find the right answer. ACT Science Research Summaries. When conducting scientific experiments, observations are made through our senses. So if you're conducting a scientific experiment, you notice or observe what's going on through your senses. Now, this is usually going to be with your sense of sight, but depending on the experiment, you may be able to incorporate your other senses. So that's what it means to observe during a scientific experiment. It means to notice what's going on through your senses. But more specifically, we can define observation as the act of noting and recording something. So this has to do with both the act of noting what's going on and then recording what happened. Because it's important for a scientist to record what goes on during the experiment so the experiment doesn't have to be conducted over and over and over again. And so to use this definition of observation, we could say the scientist is observing what's going on in the experiment. So the scientist is noticing what's going on through his or her senses, and then the scientist is recording what happened. Now, the second definition of observation is the result or record of such notation. So we don't use this definition of observation while the experiment is taking place. We would use this definition of observation as in, let's take a look at the observations the scientists made. So this is what happens after the experiment is finished and people go back and look at the observations made by the scientist. So this is more of a noun. The observations were made by the scientist. So again, one definition is the act of noting and recording something, and then the second definition is the result or record of such notation. ACT Science Conflicting Viewpoints. In order to effectively consider conflicting viewpoints, you need to be able to identify 2 things: the positions of each side of the argument and the supporting evidence for each side of the argument. So you need to understand where each side stands, and you need to understand if there's any credibility for both of the positions. In other words, understand if they have any information to back themselves up, to back their positions up. Now, a scientific dispute is a matter of fact, not opinion. So although you may feel personally more sympathetic to one side of the argument, your duty as a reader is to objectively assess the data and reasoning offered by each side. Now, each viewpoint here is trying to become a scientific claim because we have two differing viewpoints here, and so you're trying to determine which one is more credible. And so a scientific claim requires clear evidence and experimental verification before it can be accepted as fact. So when you're comparing these two viewpoints here to see which one comes out on top, you're looking for the one that has clear evidence in support of it and has experimental verification to back it up. The percent yield conveys the difference between the actual yield and the theoretical yield. Basically, the percent yield is the ratio between the actual amount of product obtained and the theoretical amount of product predicted. Because in any chemical reaction, under ideal circumstances, you're going to have one result. So that's what we call the theoretical amount. Under perfect ideal circumstances, this is the amount of product that would be obtained. Now, we're not operating under ideal circumstances, so we have the actual amount of product obtained. And so we can predict the theoretical amount of product predicted, but that doesn't mean we're going to get that. We're actually going to get the actual amount of product obtained. So that's why we have those two different terms there. And so percent yield is a way of making a ratio of comparing the difference between those two numbers. So the equation to find the percent yield is percent yield equals actual yield divided by theoretical yield times 100. And it makes sense that theoretical yield is in the denominator of this fraction because theoretical yield is going to be higher than actual yield. Now, percent yield has no units. However, actual yield and theoretical yield can have the units of grams, liters, or moles. The important thing is that actual yield and theoretical yield have the same units. So although percent yield doesn't have a unit, you need to be comparing apples to apples here and have the same units between actual yield and theoretical yield. So there are three tips that I want to share with you on how to calculate percent yield. So the first is note what you were given. So you want to take into account the amounts of reactant and product. And then second, you're going to calculate the theoretical yield. You're going to calculate the theoretical yield using stoichiometric methods and make sure that the theoretical yield and the actual yield have the same units. Then finally from here, you're going to calculate the percent yield. And again, the way you calculate the percent yield is through this equation right here. So just remember that percent yield conveys the difference between the actual yield and the theoretical yield. When a reader is required to draw conclusions from the information presented in graphs, tables, charts, or diagrams, it is important to limit these conclusions to the terms of the graphic itself. In other words, the reader should avoid extrapolating from the data to make claims that are not supportable. So consider this graph as an example. It compares the price of bread to the demand for bread. So notice here, as demand rises, price also rises, because over here, see, price is very high. Well, demand is also very high. Well, notice here, when demand is low, price is also very low. So we know here that price and demand relate to each other in some way. We can't look at this graph and say, oh, it's just coincidence that price and demand rise and fall together. No, we know there's some relation between price and demand here. But that's all we can tell from this diagram. See, we can't look at this graph and say, oh, when price rises, it causes demand to rise. We can't say that because it may be demand rising that causes price to rise. Or it could be some other variables and factors that are not included in this graph that play an important role in determining demand and price. So the important thing is when someone analyzes a graph that they don't read too far into that graphic organizer or the diagram, graph, pie chart, whatever that graphic organizer may be. It's important that the reader just take that graph at face value and only draws conclusions that are supported by the graph. A line graph is a type of visual illustration that helps show trends over time. So consider this graph right here. So we have income over here and the months of the year over here. So what we call this right here is the x-axis. This is the independent variable. This is what the constructor of this graph decided to place right here. They decided to put January, February, March, April, May, June. So this right here is called the y-axis. What's vertical is the y-axis, and this is income level for each month. Now this is called the dependent variable, because although the constructor of the graph wrote these numbers right here, when we start plotting points, the constructor of this graph didn't get to choose what the income level was going to be. They got to decide which months they wanted to have on here, but the income level is decided by what already happened. So they're not deciding the income level. So the way a graph works is, take, for example, this information we have right here. The income level in January was $1,500. So right here, we go to January, and then we're going to go up to 1,500 and put a point right there. So notice here, if someone was just looking at this graph, they could tell that the person in January made $1,500. Or they could start at the y-axis and say, okay, they made $1,500 when? In January. So we have all this information right here, and then it's being plugged into this graph to provide a more visual way for the reader to comprehend this information. Because we have all this right here, this information, but it's hard just to quickly look at this and see a trend in the income level of this person. So in January, the person made $1,500. Now in February, they made $1,000. So we're going to move over to February and then go up to $1,000. Now March, they made $1,250. So we go above March, and although $1,250 isn't anywhere on here, we can pretty much decide that since these numbers are put in increments of 500, that 250 would be found between the two. So if we go halfway in between these two, we know that the income level for March was right there. Then if we go to April, we're up to 1,500. May is 2,500, and then June is 3,500. Now to start completing this graph so that someone can understand it, is we draw lines connecting the dots. And this makes it even easier for the reader to understand the graph, because they just have to follow the lines from left to right to see the progression of income through this. Now we also need a title for this. So this could be monthly income. That would be a good title for this, because we're looking at income levels per month. So titles are good on graphs because it helps the reader just quickly look at this graph and understand what it's about. Now, see, right here we have this information, but it's hard to see a general trend of the income levels for this person over the months. This is the first half of the year, the first 6 months. So we see here that originally the income level dropped, and then it started rising. It was a steady rise from February through June, but the income level, the amount that it rose each month, increased as we got to June. So now this is a very visual way for someone to understand the information that was right here. A pie chart is very helpful for showing how a certain category is divided. So see here we have the makings of a pie chart, but it's still missing a lot. Right now all we have is information that we need to plug into this pie chart. So right here we have the expenses of Joe. So rent is $200, food is $100, gas is $50, and entertainment is $50. And this is per month. So first we need a title for this pie chart. So the title is going to be Joe's monthly expenses. So the great thing about a title is it allows the reader of the graph to quickly look at this graph, see the title, and know what this pie chart is going to pertain to. So now we first need to realize or understand how much money total is being spent. So here is $400 total. 200 plus 100 plus 50 plus 50 is 400. So we see here rent is $200. So if rent is 200, then we can reduce this down to 2 over 1, or flip it over. So here we realize the important thing is that you realize that 200 is 1/2 of 400. So if we draw a line right here, we realize that rent is half, or 50% of all of Joe's expenses. Well, food is $100, so that's a quarter of it. And then gas and entertainment are 50 each. So if this half right here represents 200 and this quarter represents 100, then $50 should represent half of a quarter, or an eighth of the total expenses. So we'll put gas here and entertainment, which I'll just abbreviate. So now you can clearly look at this pie chart and understand how the expenses are split up. Because over here you have money amounts, and that's important because someone may want to know, okay, how much is this person spending on gas? They can look, okay, $50. But what's great about this right here is it helps the reader get a visual understanding of this information up here. It helps them understand in their mind what percentage of the person's income is being spent on what. And so someone can easily see here, okay, they're spending less money on gas than they are on food, and they're spending the same amount of money that they are on gas as entertainment, and they're spending twice as much money on rent as they are on food. So it provides a very visual representation. So when making a pie chart, it's important that the writer title it, and they also need to understand what percentage of the whole each thing represents. So here someone needs to see, okay, entertainment, $50, and the total expenses are $400, and realize that 50 is 1/8 of that. So entertainment can only be 1/8 of this circle right here, because if it was a bigger area of the circle, then it would be disproportional, and it wouldn't clearly convey to the reader. So the important thing here to remember is that a pie chart is a visual way to show how a category is divided up. A table is a way to visually represent information to help the reader retain the information presented. Tables are usually presented in a standard format. The reason for a standard format is it makes reading tables easier because the reader has probably read a similar table before. So, and to comply with a standard format, a table is made up of vertical columns and horizontal rows. These vertical columns and horizontal rows combine to form cells. So you can think of it looking something like this, where you have these vertical columns and horizontal rows, and then this right here would be a cell, and this would be defined by the row number and the column number. So this would be column 2, row 2, and this over here would be column 2, row 4, and that's how the cell would be defined. And then a table is generally going to have some kind of title that helps the reader quickly identify what the table is going to be about. So it could be something like price of milk compared to demand, or average income for various education levels. If the title of the table was average income for various education levels, then the rows might be labeled education level and the columns might be labeled average income. And that would help determine what goes in the cells. So titles are very important because it helps the reader quickly identify what the table is about and determine whether or not they want to read it. But the important thing to remember about tables is that they always have a standard format of vertical columns and horizontal rows, which make cells. And the standard format makes tables easy to read and understand. Science research summaries. The science process skills include observing, hypothesizing, ordering, categorizing, comparing, inferring, applying, and communicating. These are all important science skills, and for the most part, this list goes from easiest to hardest. So if you want to understand one science skill, it's good to understand the science skills before it. So I want to go over all of these and give a brief description of each. So observing is pretty self-explanatory. This is being able to write down an accurate description of something observed in nature or something observed in an experiment. And then hypothesizing is building off an observation. You take an observation and then you form a prediction based off of that observation. Now, ordering and categorizing are similar because they both have to do with the structure of information. In ordering, you're taking information and maybe putting it in a list from most important to least important, or you're just putting it in some kind of order to make the information very accessible and very understandable. And then categorizing has to do with taking the information and putting it with other like information so that you have different categories of information. Comparing has to do with noticing the similarities between different events or different experiments. This is important because sometimes two experiments or two scientific phenomena will look totally different, but through the skill of comparing, you'll be able to notice the similarities between the two. Now, inferring is different than hypothesizing because hypothesizing is making a prediction of something that will happen, whereas inferring is making a prediction or is making a conjecture about something that did happen. It's hypothesizing is looking forward to a future event, while inferring is looking back to a past event, attempting to explain it from the information already known. Now, applying is taking a prediction and putting it into an experiment. In other words, you're taking your observation and your hypothesis of what might happen and actually applying it to an experiment. Then finally, you have communicating, which actually goes hand in hand with observing, because observing is making an accurate description of something you have seen. Well, communicating is taking those observations and being able to communicate or tell that to someone else. That may be by writing a description of it or by telling them about it. But this is very important because by being able to communicate information, scientists are able to feed off of each other's discoveries. So that's why it's important to be able to accurately communicate scientific information. So those are the science process skills. ACT, Science Data Representation. Tables are presented in standard format so that they will be easy to read and easy to understand. At the top of a table, there will be a title. And so this will be a short phrase indicating the information the table or graph intends to convey. So the title of a table could be something like price of milk compared to demand, or in this case, the average income for varying education levels. So this right here is the title. So a table is composed of vertical columns and horizontal rows. And so the information is laid out in those columns and rows. So this table in particular has 2 vertical columns and 5 horizontal rows. So this right here is a column, all of this, and then this right here is a column as well, and then we have 5 rows. So this right here is a row. Now, the actual information is placed in what we call cells, which are the boxes you see here. And so we could identify a cell by saying the cell in the second column in the 5th row. So we would go to the second column, which is this column right here, and we would go down to the 5th row. 1, 2, 3, 4, 5. So this is the cell in the second column on the 5th row. And so then there'd be information in that cell right there. And so right here we have 2 columns, and so those columns have to have labels. So we have education level and average income. So here we would have varying education levels, like no high school diploma, bachelor's degree, master's degree, doctorate, as well as associate's programs, whatever you want to put in there. And then you would have the average income to accompany each type of education level. And so I'm going to label this as well right here. That's a cell. All of these are cells. So this right here has 10 cells. And then remember that the rows run horizontally and the columns run vertically. And then you also have a phrase indicating the information that the table intends to convey, and we just call that a title. ACT, Science Data Representation. anytime you have a chart or a table, you should be asking yourself what is being shown in the data presented. In this chart, a decade's worth of data is being displayed. You see here 1980 through 1989. And it shows varying amounts of some quantity each year. So you have to ask yourself if any trends can be detected. And so as you review this chart, you will notice that there appears to be 4-year cycles in occurrence. See, right here in 1982, we have a pretty high year, and so it increased from 1981. When we go 4 years down the road to 1986, and we have another high quantity year, and that increased from 1985. And then notice here in 1982, it decreased when it moved on to 1983, and the same thing happens here in 1986. It decreases as it moves into 1987. And so we have highs and lows on this chart that are separated by 4-year intervals. So we have a 4-year cycle in effect because we have a high in 1982 and a high in 1986, 4 years apart. And then we have lows in 1980, 1984, and 1988, all 4 years apart. So this chart only goes to 1989, but if it went to 1990, we could infer that 1990 would be a high year as well. And then you should also ask yourself if there is anything remarkable about any of the data points. And so it appears here that there was an extremely low point in 1988, and so you want to try to figure out and form a hypothesis of why that is. Now, this chart isn't very specific. Generally, a chart will have a title and it will have a label for whatever these numbers stand for over here. And so if you had some more information, you could make an educated guess or a hypothesis about why 1988 was such a low year. And so that's the kind of analyzation you want to be doing whenever you're dealing with a chart or a table. You don't want to just be taking the information you're given at face value. You want to be trying to determine why the data is the way that it is. Science Research Summaries. An experiment is a set of actions and observations performed to confirm or not confirm a hypothesis or to research a causal relationship between phenomena. Now, only one condition in an experiment is changed at a time. So the conditions that affect the outcome we call variables, and then the factors in experiments that do not change are called constants. So we're dealing with variables and constants. So again, variables are the factors that do change, and constants are the variables that do not change. Now, experiments have two parts. We have the control group and the experimental group. If we just had an experimental group, we would not be able to determine anything from the observations of an experiment. That's why we need a control group, which is the group under normal conditions. So nothing unusual is done to it. And then we have the experimental group, which is the test group in which variables are changed. So the experimental group is the most important, but we have to have a control group to understand what's going on in the experimental group. So in other words, if you're changing variables here, you don't know what effect they're having because you don't have a normal group. So you start out with a group under normal conditions, and then you go to the experimental group where you only change one variable at a time. And so by changing that one variable, you get to compare the differences between the experimental group and the control group. So we're looking at cause and effect here because you have one variable that's going to cause other things to happen. So we start out with the independent variable. Which is a manipulated variable in an experiment or study whose presence or degree determines the change in the dependent variable. And so then that leads us obviously to the dependent variable, which is the observed variable in an experiment or study whose changes are determined by the presence or degree of one or more independent variables. So we have an independent variable and a dependent variable. One's manipulated and the other is observed. So the independent variable is the variable you're changing. Remember, I said you can only change one variable. So you're changing the independent variable, and we're looking at cause and effect. So the independent variable causes an effect with the dependent variable. So that's what you're looking at here, the cause and effect between the independent and dependent variables.